Okay, so now that we know what nuclear chemistry is, let's talk about how this actually works. All right, so what happens when the nucleus breaks apart? So, there are many elements that are actually naturally unstable and regularly just automatically go through nuclear decay. So they have unstable nuclei and will spontaneously nuclear react. And we call those elements radioactive. Right? The reason why this happens is because the strong nuclear force works really, really well, but over short distances. And it does require a certain ratio of protons to neutrons to really stabilize the nuclear force. So, sometimes when atoms get too big, or if they have just an off-kilter ratio of protons to neutrons, the repelling force of the protons can overcome that strong nuclear force and burst the nucleus apart, causing a spontaneous nuclear reaction. So, just thinking about maybe things you've seen in movies, or if you've done any research on like nuclear reactors or things like that, can you name any radioactive elements? Right? If you came up with things like uranium or plutonium or something like that, you were spot on. Those are some pretty common ones that people have generally heard of. So, radioactive decay will always release energy and usually some particles. So, here's just a few examples. When reacting, the nucleus might release an alpha particle via what we call alpha emission. All right, so that alpha particle is a helium nucleus that has 2 protons and 2 neutrons. All right, or there's beta emission, where a high-speed electron is released, or gamma emission, where light, really high energy light or electromagnetic wave is released. All right, and that last one is pretty dangerous. So look at this picture down at the bottom here. What do you think this is showing us? All right, based on that picture, which particle do you think is more dangerous? The alpha particle, the beta particle, or the gamma ray? So what this picture is showing you is that, okay, an alpha particle has been released in a nuclear reaction, and it ran into a piece of paper, it's done, it can't move any further. The paper blocks it. All right, a beta particle gets released, it's going to pass through the paper, but if it comes up to something like aluminum foil, it'll stop there. Gamma rays, though, on the other hand, that's going to go right through the paper, right through the foil. It's going to go right through your skin if you were in the way. And the only thing that's really going to stop it is lead or concrete. All right, so this is showing you that gamma rays really strong. It can go through most materials. All right, so if you recall maybe sitting in the dentist chair getting your x-rays done, they usually make you put on that big heavy apron. All right, what that is it's a lead lined apron. That's why it's so heavy, to protect you from the gamma rays that are being given off by the x-ray machine. All right, so this is an important slide. I highly recommend spending some time with this. If you need to, play this slide again. But this is kind of showing you what these reactions look like. All right, there's also some trends to what types of nuclei go through these different kinds of radioactive decay. So like, for example, alpha emission. That is something that is predominantly done by large unstable nuclei, right? Which kind of makes sense because in alpha particle, you're giving away 2 protons and 2 neutrons. You gotta have enough of them there for that to really be easy to give away. All right? When you are dealing with a reaction, all right, you're going to see that your mass decreases by 4 and your atomic number decreases by 2. All right, and then you've got your alpha particle that gets given off. Beta emission, on the other hand, is for smaller nuclei, but they have a ratio of neutrons to protons where there's really too many neutrons. All right, so what will happen is one of those neutrons will decay into a proton. So what you'll see in a reaction for beta emission is that your mass stays the same, right? Because you're just taking a neutron and turning it into a proton. So that still factors into that mass calculation. All right, but your atomic number is going to increase because now you have an extra proton. And, of course, that's going to change the element. And then these give off beta particles. And that's what this symbol stands for, is your beta particle. Another option for smaller nuclei, but this time if they have too many protons, is they can convert that proton into a neutron. All right, and you can do this a couple different ways. There's electron capture. All right, and that's going to require an electron from the electron cloud to come in. It kind of fuses with the proton so that it can decay into a neutron. All right, so there's your electron coming in there, and you can see that your mass stays the same. Proton number goes down, right? We're getting rid of an extra proton there. There's also an option that doesn't require the electron. All right, you'll see the same thing. Your proton number goes down, your mass stays the same. All right, but this gives off a positron or an anti-electron when that happens. So again, I really do recommend getting a copy of this, using it as kind of a guide to picking apart a question so that you can, you might be asked, like, which of the following would be given off by alpha emission, or what would happen if you had too many protons, right? So this is going to be a good slide to have out when you are taking tests and quizzes. All right, so there are the different types of radioactive decay. Now let's talk about half-life. So radioactive decay occurs at consistent rates, all right? But those rates are different depending on the element or the type of decay you're dealing with, all right? So like uranium decays at a different rate than plutonium, which decays at a different rate than carbon-14, all right? So scientists came up with a way to address these rates, and they called it half-life because of how they figured out how to measure it, right? That term half-life kind of tells you what you're doing. It's the amount of time for half of your sample to decay, all right? So if you had 10 grams of uranium and you wanted to figure out what the half-life of uranium is, you would sit there and you would time how long it takes for 5 grams or half of it to decay, and then you'd have its half-life. All right, some of these half-lives are insanely long. All right, carbon-14 has a half-life of 5,750 years, and that's not even the longest one. There are some things that are given off by nuclear reactors that take hundreds of thousands of years to decay. All right, so depending on what you're using, half-life can actually come in really handy. Like carbon-14 we use for fossil dating, right? Based on how much carbon-14 is left in the bones, you can figure out when those bones were deposited in the ground. Things like that. So you will need to be able to do some basic half-life calculations, all right? So couple different things you can do. You can figure out how much will be left after a certain number of half-lives. So that's what this kind of question is asking you. It says you have 10 grams of a substance that decays with a half-life of 14 days. how much will you have after 70 days? All right, and when I do these, I like to set up just kind of a little table. All right, so I have my sample, and I have time. At time 0, I have 10 grams. All right, let's let one half-life go. So 14 days pass. Now I've got 5 grams. Let's do another half-life, so another 14 days, which means 28. I'm gonna have 2.5 grams. All right, and then if I add 14 to that again for a third half-life, that is gonna be 42 and 1.25 grams. All right, and then another one is gonna bring me up to 56, which will be 0.62-ish grams. And last, one more half-life gets me to 70, so I would have 0.31 grams. All right? So any sort of calculation you have to do is going to be like a whole number of half-lives, but take your time. All right? Write out a table. Because I would say the most common issue that I see is people that end up going either one half-life too far or they're short one half-life. All right, so if you set up a little table like this, you should come to the appropriate conclusion. Another example of a type of calculation you might have is you can figure out how many half-lives have passed based on how much you have left. All right, so say you had 12 grams of a substance and it has a half-life of 2 days. How many half-lives passed if now you only have 0.75? All right, so again, I've got 12, sample, time, 6, in 2 days, in 4 days I'll have 3, in 6 days I'll have 1.5, and in 8 days I'll have 0.75. So 8 days has gone by.